Hi everyone. In this tutorial, we're going to cover backpropagation. So this is something I said I would talk about earlier in the course, but I didn't get time to. So I thought this would be a good time to go back and discuss it. And before I kind of jump into uh, neural networks and backprop, I just want to revisit the chain rule for differentiation that we saw, I think, in the first video of the course. So remember, if we have a function, let's say h of x, which is a function of a function. So something like this. So this is called a composition of functions, right? And we want to try to differentiate h with respect to x. Okay, the chain rule tells us that we can basically differentiate the first function with respect to the second function multiplied by the first function differentiated by its argument dx. Okay, and so another way to write this is f prime of g of x times g prime of x. Okay, so for example, let's just do a really simple example. Let's say h of x equals to e to the power of x squared. Okay, so you can think of this as a composition of two functions. The first function is just the exponential function, and that has derivative e of x, right? The exponential has the derivative, which is exactly the same as the original function. And g of x, well, it's the function up here. G of x is x squared, and then g prime of x is 2x. Okay, so the derivative of h is going to be f prime of g of x times times g prime of x. So that's going to be, so f prime is going to be the exponential evaluated at g of x, okay, times g prime of x. So this is going to be e to the power of g of x, which is just x squared, times g prime of x, which is 2x. Okay, so this is the chain rule in action, and you can actually have the chain rule for any number of compositions. So this is just a composition of two functions, but we can also have a function that looks like f of g of t of x, for example. Okay, and we want to compute the derivative with respect to x again. I'll just write this as h prime of x. Well, this is going to be, again, we're going to apply the same, this is why it's called the chain rule, because we can chain, we can chain a bunch of functions. The chain rule gives us kind of a similar result. This would be f prime evaluated at now the entirety of the argument times g prime evaluated at its inner argument times t prime of x. And to prove this, you basically just, use the chain rule from here to evaluate the derivative of this inside guy. So you can call this inside guy, say, k of x. Use the chain rule on f of k of x, and then you would get the derivative of k of x at some point, and then you have to evaluate the derivative of that using the chain rule, and so you would get this. Okay, but basically it's pretty intuitive just to see it from here as well. So if I had a function, let's just do an example as well. If I had a function e of, say, 2x plus 3 cubed. Okay, so in this case, we still have f of x being the exponential function. So same derivative. We have g of x as kind of the second function in the hierarchy. So the second function is, you could look at it as this thing to the power of 3, so x cubed. Okay, then g prime is 3x squared. And finally, t of x is 2x plus 3, so t prime of x is just 2. So the derivative h prime of x using our chain rule is going to be f prime, so e to the power of the entire g of t of x, which is 2x plus 3 cubed. So this is g of t of x, multiplied by g prime of t of x. So g prime is 3x squared, so evaluated at t of x, it's going to be 3 something squared, and inside here goes t of x, which is 2x plus 3. Finally multiplied by t prime of x, which is just 2. So this would be 6 2x plus 3 to the power of 2, e to the power of 2x plus 3 cubed. Okay, and hopefully you should see that, basically the chain rule lets us evaluate these really ugly looking functions by breaking it up into really smaller, easier pieces to manage. And the derivative looks really complicated, but actually all we're doing is just taking derivatives of really simple functions f, g, and t. Okay, and so you might ask yourself, why am I talking about the chain rule? Well, backpropagation is just chain rule, right? This is just a pretty much just a fancy term for so chain rule on graphs. Okay, so you can think of neural networks as a big graph, and so backpropagation is just the name of how do we compute gradients, how do we compute derivatives in order to do learning for these giant neural networks. Okay, so let's actually review what we've seen so far. So in the previous video, I looked at perceptrons. Okay, and we said that a perceptron was a single unit. It has a bunch of inputs, right? So you have your x, it goes in here. Each of these guys are a weight, W0, W1, W2, W3, maybe all the way down to WP. Inside here, what do you compute? You compute the summation Wi xi, okay? And then you have an activation function. So I didn't call it an activation function last time. I basically just called this a, we called it a sign function. Okay, so this perceptron computes the weighted sum, takes the sign, and then outputs a +1 or a -1. Okay, that was the idea of the perceptron. At the end of the video, I said that I introduced the idea of gradient descent. Okay, and the idea of gradient descent is that if you want to minimize a function, right, we want to pick the x, we can basically pick a value of x and minus the gradient take steps in the direction that minimizes the function, which is the negative of the derivative, and usually we multiply by some parameter eta or alpha, which is called the learning rate or the step size. Okay, and the idea was basically how do we try to learn a perceptron or try to compute these weights using gradient descent. Remember, the perceptron algorithm gives us a way of computing the weights, but we said we want to try to use gradient descent to do this thing and to do this learning. And so we basically walked into the problem of having this function, right? So this function, the sign function, is a step function that looks like this, right? And sorry, I keep drawing it incorrectly. It looks like this. Okay, so there's this massive gap, which means that this function is discontinuous, right? It doesn't have a derivative, so we can't actually compute gradients. And so that motivated us to use the sigmoid function, or introduce the sigmoid unit. Okay, so the perceptron, you can think of this as a single unit. The sigmoid unit is the sigmoid unit, or sigmoid perceptron, which basically has the same structure. Okay, still computes wi xi, but now instead of passing it into the sine function, passes it into the sigmoid function. Okay, I'm going to use w transpose xi instead of the sum just to make my life easier. Okay, so the activation function now is the sigmoid, and this gives us a number between 0 and 1, and but depending on the size gives us a classification. So anything above 0.5 you can take it as a +1. Anything below that, below 0.5 you can take it as a -1 if you're doing a binary classification task. Okay, so this is pretty much what we got up to last time, and the reason we wanted to use this sigmoid function is the sigmoid, and again, this is sometimes called the logistic sigmoid, by the way, logistic sigmoid, is 1 plus e to the power of -x. Okay, and the derivative has a really nice form, which looks like this. Okay, so the idea is that we start off with a perceptron. It gives us a nice algorithm to do things with, but it has a problem. The problem is that when you have a different approach where you're trying to minimize a loss function, this thing doesn't work anymore because you can't get gradients. So you propose a sigmoid unit, so you can make use of things like gradient descent to minimize the loss. Okay, and the sigmoid, the logistic sigmoid, is this function here, and it has derivative like this. Now this is kind of old school. Logistic sigmoid isn't as widely used anymore in deep learning. In deep learning, they tend to use something called the ReLU. Okay, there's also hyperbolic tangent activation functions. Whatever, it doesn't really matter for our purposes. These are basically proposed because they kind of help the engineering process as far as actually getting results and making layers, making neural networks deeper and deeper. But for our purposes, we're going to stick to this kind of I'd call it old school. Nobody really uses this anymore, but it's nice. It has an easy derivative, and it will do the job as far as explaining the algorithm backpropagation. Okay, but just keep in mind that that we use different activation functions in practice. Okay, so that's basically where we got to last time, and then I said, okay, well, the perceptron is a single unit and is quite limited. It's a linear classifier, right? It's quite limited in what it can learn, and so sometimes you want to expand the capability of the model, and one way to do that is to add more perceptrons and build something called a multi-layer perceptron or a neural network. Okay, so multi-layer perceptron, but I'm going to start calling it neural network because MLP is a very outdated term. Is basically just a combination of a bunch of different single unit perceptrons into a bigger structure. Okay, so I'm going to try my best to explain backpropagation and make it rigorous. I think the reason it's actually pretty hard to find really good explanations of backprop, in my opinion. The reason is it's quite messy. It's not difficult mathematically, but it's just quite messy to keep track of all the different indices, and the fact that neural networks can have a lot of different architectures makes it even harder to kind of give one general algorithm. So I'm going to try my best today to try to give one generalized algorithm. So the idea is that as usual, we have our data set, which is composed of XY pairs. And I'm going to assume that we have each xi is going to be a vector. So, this shouldn't be anything new. Each xi is a vector, but I'm also going to assume that yi can also be a vector like this. Okay, so we have our data set, xy pairs. X is a vector in p dimensions, so this is how many features we have, and our output yi is a k-dimensional vector. Okay, and so that means that for example, if you're trying to predict, if you have a multi-class problem, right? So if you're trying to predict one of k labels, this kind of network can do that for you. Okay, now how do we actually visualize this thing? Okay, and the way I like to visualize it is to have to draw out the layers. So I'm going to have input layer. I'm going to have a hidden layer 1, maybe hidden layer 2. Okay. In my input layer, okay, well, if my inputs are these xi's, right? These are, the input layer is where I put my inputs. If they're p-dimensional, then I'm going to have p sites or p inputs. Okay, and usually we'll have an extra input called the one input. Okay, so this is going to be 1, 2, p plus 1. And you probably guessed exactly what this means. P plus 1 is just like linear regression. The extra 1 term here is just for a bias. Okay. And in the hidden layer, we have our neurons or our perceptrons or our units, whatever you want to call them. Usually, because this is a hidden layer, we'll call this a hidden unit. Okay, and I'm going to draw a bunch of hidden units. Okay, and actually, we're also going to have a bias in this layer here. Okay, so if my, this is up to you to pick, but let's just say we have H1 hidden units. And I mean H1 as in H1 hidden layer 1 number of units. Okay, so this is going to be 1, 2 down to H1, and then this is H1 plus 1. Okay, now H1 varies depending on what kind of architecture you're building. You've probably played around with TensorFlow or PyTorch. You can pick the number of hidden layers. Like you can't pick the input layer, you can't pick the output layer, but you can pick the number of hidden layers to be any number that you want. Okay, so I'm just going to assume it's just some general H1. Now, between the, hidden layer, so hidden layer 2 is going to have H2 units. This can be different to H1. So here we're going to have a bunch more units. And again, we're going to have some bias variable here. Okay, so in between each layer is a set of connections. Okay, so the input side, the first input side, so by the way, xi, right, is xi1, xi2, up to xip. So you can think of this as your features. Okay, so the first input side takes the first element of the feature vector, so xi1. Okay, and basically what we have is a connection, and the weight of the connection is labeled. I'm going to use this labeling. Sorry, let me make that clearer. 1, 1. Okay, and so let me just explain what this means, right? The W11 is, so maybe I can put it here. wji for this means the weight connecting ith input to jth node in kth layer. Okay, so maybe this is not the best numbering, so here I could maybe say this is W1, but for now we'll just keep it like this. I just mean that between every two layers, okay, so I'll call this the first layer, the second layer, the third layer. Between every two layers, we're going to have a set of weights. Okay, the layer number is going to be this number in brackets. The node that's receiving the weight, okay, so here this is the first node in the first hidden layer, is going to be the first subscript, okay? So that's why, you know, this is node 1, node 2, node h1. That's why in these weights, the first element is 1, 2, h1, okay? And I'm just going to try to keep it really clean. That's why I keep erasing things, because this can get pretty messy pretty quick. Okay, and the second subscript is the subscript telling us which input it's coming from. So for example, they're all coming from the first input here, right? So the second subscript is 1. If I was going to look at this guy, the connection from here to here would be W0 H1 P. Okay, or if I was looking at this guy, this would be W0 H1 P plus 1. Okay. Now, we don't connect the first layer to the bias of the next layer, okay? So we connect the bias in the previous layer to everything in the, so this gets connected to everything. So we have, this is node 2, P plus 1. Okay, so the bias gets connected to everything to the next layer, but we don't connect the previous layer to the bias of the next layer, okay? So there's nothing incoming to this guy. Okay, so what does this tell us? Well, it tells us that, you know, the first feature, xi1, gets connected to every single node in the next layer. So you see how it's getting passed to every single node in the hidden layer 1. Okay, and similarly, the second feature gets passed to all of those. The pth feature gets passed to everything, and the bias gets passed to everything as well. Okay, so between the input layer and the hidden layer, okay, with h1 units, we can actually count the number of weights. We're going to have p plus 1 times h1 total weights, right? Because every single, so we have p plus 1 inputs, each one has h1 connections, so that means p plus 1 h1 total weights. And so you can kind of see already the problem with neural networks is they have an incredibly large number of weights. And so when it comes to training these things, right, how do we train? Think of regression. How do we train regression? We take a derivative and we set that equal to 0 and compute the weight, right? That's no longer going to be possible because this thing has so many weights, it's really hard to get a closed form solution, as we'll see in a minute. Okay, so this is the idea of, this is why we need backpropagation. Backpropagation is the algorithm that tells us how to train a neural network. Okay. All right, so we haven't finished describing what the neural network does yet. We've just described what happens in the first layer. The next thing to do is to try to describe, let me use a different color, try to describe what happens once it gets to the this node. So you can think of this guy exactly the same way we thought about the sigmoid unit. Okay, so this first unit is receiving a bunch of inputs. In fact, it's receiving the p plus 1 inputs. It computes the summation, which we'll call net 1, 1. I'll explain what this terminology means in a minute. And this is the sum. Let's say j equals 1 to p plus 1, w1j 0, and let me call this output of 0j. Okay, so let me just explain what I've done here. The first unit just takes all the inputs it's getting. Okay, and I've called these inputs oj0. And so let me just explain. So xi is going to the network. Sorry. Let me write xi equals to O0. Okay. The reason I'm using this notation is because the best way to think about a neural network is that we have an input, right? It goes into one layer, some computation happens, and then that computation, the output of the first hidden layer becomes the input to the second layer, okay? So I'm just treating the first initial input as kind of the output of the first layer, if that kind of makes sense, right? So I'm just rewriting xi, the original data input, as the 0th output, okay? And so what the first unit is doing is computing this weighted combination of the weights that go to that network multiplied by the outputs of the input layer, which is just the input itself, okay? And as I do more and more of these, this should become pretty comfortable. And basically what it does is computes this sum. It passes it into, let me just write it under here. It passes it into the next step, which computes the sigmoid of that sum. Okay, now then this becomes the new site, and this one gets passed into the next layer, and we're going to call these guys the weights 1, 1, 2, 1, 3, 1, and this is going to be H2, 1. Okay, and so what I want to just explain here is that all we're doing is repeating what we did initially. The only thing that's changed is that the layer number has gone from 0 to 1, okay? And the input, we're kind of treating the hidden layer 1 as our new input site, okay? So you can think of these guys as the new inputs, and I can call these in this case, I'll call this O11. Okay, which means it's the out, because I'm calling the the initial input O01. This is the output of the first layer. The second layer computes sigma net 1, 2, and that's going to be the output of the first layer, or the second output of the first layer rather. And similarly, this guy down here is going to compute sigma net 1 H1, and this is going to be the H1 output of the first layer. Okay, and again, all of these guys get connected. So this one gets connected to all the inputs. This guy gets connected to all the inputs, and so does the bias term, gets connected to all the inputs. Okay, and we start all over again. We compute, we can do it here. This guy here computes sigma of net 2, 1, and we'll call that output O1, 2. This computes 022, and so on and so forth. Okay, so this already looks quite messy, but the idea is quite, hopefully quite easy. Each network looks at the weights connected to it, looks at the inputs from the previous layer, computes this weighted sum, takes a sigmoid of that, and then treats that as its thing that it's passing on. The second layer looks back, does exactly the same thing with new weights, computes its weighted combination, takes a sigmoid, passes it on. And you can do this for as many layers as you like. And the idea with deep learning is that the number of hidden layers is huge. The width of the width, as in the number of units in each hidden layer, is also huge. So you can think of the the number of weights is growing quite, it's becoming quite big as you take a deeper network with wider layers. So in this, just to make this concrete, the number of weights that we're going to have here is going to be h1 plus 1 times h2, right? And you keep, you can basically, to get the entire weights of the network, you just keep adding along these total weights. So when I say total weights, I mean total weights in this particular layer, okay? And the reason, again, I want to keep using this notation, I want you to think of every single neuron or every single unit as having its own output, okay? And its own output becomes the input to the second layer, and the output of the second layer networks becomes the input to the third layer, and so on and so forth. All right, so maybe pause this video, try to draw this picture for yourself. The hardest part about this really is just getting a hang of the indexing. It's really annoying to keep track of, and it's really hard to actually explain this on paper. So just make sure you're comfortable with that. All right, so let's, I wanted to draw this all on the same page, but I don't think I'll fit it. Just imagine that we're, well, let me actually just draw the continuation. So this was hidden layer 2. We had H2 units and the bias. Okay, and we're going to keep doing this until we get to some number of hidden layers that we specified. So I'll call this hidden layer M. M could be any number that you like. This is going to have HM units. Okay, and let me draw the mth hidden layer. And this is the last hidden layer. You can choose it to be any number you like, but this is the last one. And the very last thing we have in our neural network is the output layer, or the output, the output units. Okay, and remember, the way I set this up was that we had an output of dimension k. So this output needs to be k units. Okay, and this is going to be 1, 2, 3, all the way to k. We don't need a bias. We don't need a bias anymore for the output unit. Okay, and these guys are called the k output units. Now between the last layer, this last hidden layer, we're still going to have these weights, 1, 1, but these are now going to be the mth layer. Okay, so nothing changes. I'll just draw them for the one connecting to the top. So this would be W12M. This is unit HM, so this would be W1HM. Okay, and this one is W1HM plus 1. Okay, again, they all have the same superscript M because this is the mth layer. Okay, so we know what happens in the output unit. The output unit is going to compute O1 equals to sigma net 1 output. Okay, and this is going to compute O2 sigma net 2 output. Okay, and just to clarify, right, I'm using here net 1 output. Before I was using sorry, I think I've mixed these up. Okay, I should, just for consistency, I want to keep it net output 1, net output 2, O3 is going to be sigma net output 3, and OK is going to be sigma net output K. Okay, and just going back to the first layer, right? What happened in the first layer? We computed the output here, right? As we called it O1 superscript 1. So here I'm just saying O1 without any superscript is referring to those output units, okay? And the net is just the summation of the weighted combination of the outputs of the previous layer. So this would be sigma of the sum, j equals 1 to hm plus 1 of the weighted combination, so w 1j, okay, multiplied by the outputs of the previous layer. Okay, we know that this guy is going to compute an output, and that output is going to be called output 1 for the nth layer. Okay, so this guy is just taking those outputs from the previous layer, taking a weighted combination, and taking the sigmoid of them. Okay, so everything is the same from layer to layer. All that's really changing is the indexing, right? And the number of hidden units can change. Okay, but the general idea is the same. Now, what happens at the output layer is you can think of all of these guys leading into, so let me just explain. O1 to OK, that's your output, right? So if you're trying to predict, if you're predicting y, okay, then your prediction y hat is equal to this vector O1 to OK, right? So to compute the loss, I haven't given myself much space, but so I'm just assuming these guys are coming into together, and I'm going to compute the loss, which is the loss is going to be mean squared error, so half so let me use this notation, y minus y hat squared, and we're going to sum over all d data points. Okay, d equals 1. Okay, and that's basically the neural network and how it basically takes input and produces output. And the loss function is, in this case, mean squared error. It's going to be the squared difference of the truth, which is yd, minus the predicted value y hat. And another way to write this down, let me write it on a different page. Okay, so let me just rewrite the entire loss function. So this would be, okay, number of data points. So when I write this, it just means the number of data points, so bar d bar. Okay, and we can actually expand this out. Okay, so what does this mean? this means that you take every element of yd and y hat d and you minus them and take the square, right? So, and then you sum over all those points. So this is going to be the sum from k equals 1 to k of y dk minus y hat dk squared. And you can think of y hat dk squared is just the thing that we predicted, right? So what is the thing that we predicted? It's going to be O dk. And so I know I've kind of changed things up a little bit here. I'm writing d because I'm looking at all the data points, and ODK would be the, so, every time I put an input xi into the network, I'm going to get a prediction, okay? And here I've just called it O1, O2, O3. I'm going to get different predictions for every single different input. So the first input is going to have, O11, O12, O13, etc. So here I'm just taking, I'm taking account of that for different inputs I'm going to get different outputs. And the total loss of the network is going to be this value here, summing over all data points, summing over all features, the difference between the truth and the predicted value squared. Okay, so this is basically what a neural network does, and the only difficult part, as I said, is keeping track of these indices. Hopefully everything else is pretty clear, but I just want to note a few points. This W is the vector of all weights in the network, right? So these outputs here, right? If we just look at this network, right? These outputs O1 are a function of the weights in the previous layer, right? And the output of the previous layer. The output of the previous layer is a function of the weights in the previous layer to that times the output of the previous layer to that, etc., etc. So you get this chain of computation that happens. And so when we're talking about weights, the weights of the neural network are this gigantic vector, which is all weights in the first layer, all the weights we had, which was everything from 1, 1, 0 to H1 P plus 1. Then you look at the weights in the second, in the first layer between the first two hidden layers. You'd have 1, 1, and everything up to the mth layer, 1, 1, and you keep going. Okay, so this weight vector is all weights in the network. Okay, everything from the weights in this layer to the weights in this layer to the weights in the last layer. Okay, we have to basically be able to tune those weights in order to get the network actually predicting reasonably. All right, so at this point, I just want to mention something just as an aside. Okay, you can think of building this matrix that combines. So for each layer, just put all the weights in a single matrix, right? So W0 could be the matrix of right. The way we've set up these indices are actually meant for usage in matrix. So matrix notation is row by column. So you can think of every row as the weight of the previous layer to the first node in the second layer. Okay, this is going to be W0, 2, 2, W0, 2, P plus 1, and so on. Okay, let me just write them all out. Okay, so why would we want to do this? Well, if you're trying to build a neural network class from scratch, you probably wouldn't do that because there's really good implementations that are much faster than what you'll probably come up with. But if you were going to do it, the way you do it is using matrices to collect the weights. And so you can think of, let's just go back to the first thing that's being calculated here, net 1, 1. Okay. So the output, the first output, right, from the hidden layer, the first hidden layer, is this guy, which was the sigmoid of the summation of the weights connecting the input layer to the first layer, okay, multiplied by the outputs of the input layer, which again, the outputs of the input layer are just the inputs, okay, but I'm going to use this notation to keep it consistent when I'm talking about this O variable. Okay, so what exactly is this guy? Well, this is the sigmoid of the first element of the matrix product W0 times the vector output 0. Okay, where output 0 is just all the output elements of the zeroth of the zeroth input and 1 at the bottom. Okay, so if you think of taking the matrix product of this W0 with this input, right, what do you get? Well, the first product, right, the first element is you take this row, the first row, and you multiply it by the elements of the vector. And so what you get is the summation of these guys multiplied by these guys, which is exactly the net 1, 1. Okay, and so here's what I've said. I said it's the first element of that matrix product. And then when I say, so let me just get rid of this, keep it neat. So when I'm taking the sigmoid, I'm just taking the sigmoid of this first element. And then similarly, the second output, so again, let me go back here. Okay, the second node in the first hidden layer has output 021, right? So this guy is going to be the summation. Now it's going to be sorry, by the way, this is not Wij, this is W1j, but in this case we have W2j, 0, OJ, 0. And so this is going to be, you can probably guess, it's going to be the second row, right, multiplied by that vector O0. So this is going to be second element of the vector, the matrix product W0 times O0. Okay, in other words, the vector O1, right? Remember the vector, for this layer, we're going to have H1 outputs, right? So we can actually just compute the entirety of that output by just computing the matrix product, W0 times O0. Right, so if you were actually building this thing in Python, you wouldn't want to compute, you wouldn't want to write code to try to compute, like a giant for loop for every single hidden node. What is the output, right? You would just combine all the weights in a single array, all the outputs from the previous layer in a single vector, and then you would just, to compute the output of that particular layer, you would just take the matrix product of those two guys. Okay. Now there's a subtlety here I want you to be aware of if you're actually going to try to implement this. I'm actually going to call this O hat 1, okay, instead of O1. And the reason is if you look at this guy, W0, this is a matrix of H1 by P plus 1, right? So the shape of this matrix is this dimension. The shape of O0 is P plus 1 times 1, right? It's just a vector with P plus 1 elements. P plus 1 because we have P features, and the 1 is for the bias. Okay, so this is going to be a vector in, remember, to compute the size of a matrix product, the inner values have to be the same, right? P plus 1, P plus 1, they have to be the same, otherwise you cannot multiply those two matrices together. And the resulting the resulting vector or matrix or whatever it is has dimension equal to the first element here and the second element here. So H1 times 1. Okay, and if if you're paying attention, you should see that this is slightly problematic because from the first layer to the second layer, okay, we're going to need an extra set of weights for the bias, right? So what we do is let me repeat that. What I mean is that the hidden layer here has H1 units, right? These circles are H1 many. But to go to the next layer, we're going to have this extra bias term. Okay, so to account for that, we actually need to build O1 as the concatenation of O hat 1 and 1, right? And now this is going to be an H1 plus 1 vector. Okay. Now I'm just going to do it here just to keep it all on the same page. The output hat for the second layer, for the second hidden layer, is going to be the sigmoid sorry, by the way, I'm missing the sigmoid here. And by the way, when you see this in numerical computation, when you see the sigmoid of a vector, that just means element-wise. So it means that you take the sigmoid of every single element in that vector, okay? Because the sigmoid is actually just a function that acts on a one-dimensional input, but here we have a H1 dimensional input. So when you see this happens a lot in deep learning. Make sure you understand that this is an element-wise function of each of the dimensions inside of that inside of the argument. Anyway, so the output hat of the second layer is again similarly going to be W1, and this matrix is going to be the same as W0, except that we're going to replace all the subscript by 1, right? The superscript, not the subscript, by 1, because they are now the weights in that second in the layer between the two hidden layers. And so this is going to be multiplied by the output of the layer before it. Okay, and then same problem, we define O2 as the O hat 2 and 1. Okay, and this is going to be H2 plus 1, a vector in H2 plus 1 times 1. Okay, so this is really just an aside. You don't really need to pay too much attention to this at the moment. I just want to kind of explain to you that usually you don't try to think of each of these weights on their own. You try to put them into a matrix and work with that, work with the matrix products, and you can compute. Basically what we're doing is going from basically what we're doing is at each step taking a further, so let me just do input, hidden 1, hidden 2, hidden 3. So what is a neural network? Well, a neural network is, we start off with some base output, which is, just our input. and then we compute a first layer output, which is equal to the sigmoid of some set of weights multiplied by the base output. And just to be technically correct, we actually concatenate this like this. Okay, and then we pass that along into a second layer. Then we compute the second input, which is the sigmoid of the second set of weights with the previous output concatenated with 1, and so on and so forth, right? So if you go back to the way I started this tutorial, I was talking about the chain rule. Well, the reason I'm talking about the chain rule is if you think about the output, so this, when I say O, when I talk about O, this means the output in the output layer, the final layer. What is this? Well, this is the sigma times the weights matrix in the previous layer, which is layer M, multiplied by the output in layer M. But using this definition, we actually have this recursion where we can rewrite the output M as this vector O hat M1, okay? And we can simplify that, well, not simplify, we can actually expand out O hat M as being the sigmoid of the weight matrix before it times the output before it. Okay, and this again is equal to, so we can keep going, right? We can keep, I'll do it for one more step. This is going to be okay, this is going to get pretty ugly, but I'm just going to do it anyway just to show you the dependence. Okay, so I mean, this is not something you need to write down. I just want to kind of show you that the output in the final layer, right? The output in the final layer is a function of all those weights, right? Because it's the function of Wm, Wm minus 1, Wm minus 2, all the way down to W0. Okay, so why do I talk about chain rule? Well, because what we need to do learning is gradients, and we need gradients with respect to the weights. And to compute the gradient of the weight in a layer, deep inside the network, the only way to do that is to use chain rule, right? Because, it's really, really hard to do this derivative. So we're going to try to break this up into a composition of functions, simpler functions, and take derivatives of those in order to be able to do any kind of learning. Okay, so hopefully at this point you're just kind of comfortable with the idea behind the forward step of a neural network. The forward step of a neural network is to plug an input in here, and at each layer compute an output. Okay, so each node has its own output, and the final output is just this, is just these guys, and the loss function we use is just this mean squared error. Okay, and the mean squared error can be written explicitly like this. Okay. Now, how do we train a neural network? Well, the only way to do this is numerically, right? Because it's really, really hard to take derivatives. I mean, you can imagine with, when we had linear regression, right? We had y hat equals to w transpose x, right? And then we had our loss function, okay, which looked like this, y hat I minus yi squared. We took derivatives, and we set them equal to 0, and we solved, and we got the solution w equals to x transpose x. inverse x transpose y. Okay, that is not going to happen for neural networks. Neural networks are far too difficult. There's two reasons for that. The first reason is well, actually, there's only one reason for that. The reason is that we have the sigmoid function, which makes finding a closed form solution very difficult. So the only way we really are able to try to minimize the loss is by gradient descent or other numerical techniques. Okay, so gradient descent we're going to have to come up with a scheme in which we update the weights. Okay, and the update is actually really simple. If you've watched the previous tutorial on gradient descent, it's the previous weight plus minus eta times the gradient of the loss with respect to that weight. Okay, so it's pretty simple, right? We look at the loss functions, right? The loss function here. We know that the output ODK is a function of all the weights in the network, and we want to compute the derivative of the loss function with respect to every single weight, and then update every single weight using this update step. Okay, so the hard part is computing this guy, right, for every single weight in the matrix. Every single weight in the network. This is gradient descent. What I'm going to walk through is called stochastic gradient descent. Okay, and in stochastic gradient descent, the loss, we don't compute the entire loss, okay? We actually just compute the loss on a single data point. And so the update is basically the same thing, but instead of computing the loss on the entirety of the data set, I'm just going to compute the loss on a single input. Okay, and I just want to mention it here. You know, we usually use batch gradient descent or batch training, and in this case, you know, what does LD W mean? It just means that we compute the loss function over a set of data points D. Let me see the notation I used here. Okay, YDK. Okay, where D is a set of points which is smaller than the entire data set. So like batch means just a batch of data points. So here it's like 3 data points. So instead of like computing so in order to compute this loss function, I would have to pass the entire data set through the network, compute the prediction for every single input point in my data, okay? And that could be really, really expensive if I have a very large data set. So instead what I could do, so instead of waiting to go through the entirety of the data set before updating my weights, what I could do is just compute this sum over 5 or 20 or 100 data points, okay, and then do an update. And the reason that's useful is if you're only doing weight updates every, say, million, like if you have 1,000,000 data points, then you're only doing weight updates after doing 1,000,000 passes through the network, which is way too slow. So batch gradient descent is saying you can kind of approximate the loss function by looking at the loss over a smaller number of randomly sampled data points. So the data points have to be randomly sampled for this thing to work. And stochastic gradient descent is where we just do it over a single data point. So this is just the loss associated with a single data point. And the reason I'm going to walk through this particular approach is it just makes the math slightly less tedious, right? But you can basically redo the math for gradient descent or batch gradient descent, and all that changes is that we sum over multiple data points. Okay, but this is the one I'm going to do. This just means that we pass a single input through the network, we compute the loss on that input, we update all the weights in the network. Okay, so let's actually walk through how we would compute these derivatives. Okay, and this is the idea, or this is backpropagation. Okay, so we want to be able to okay, so let's start off with case. So there's actually two cases. The first case is the simpler one. It's the case where, so again, the goal for the rest of this video is to compute the loss, the gradient of the loss with respect to the weight Wji. Okay. Now the first case is where Wji is Wji m, which means that this is a output layer weight. Okay, so if we go back to the picture of the output layer, okay, the weights in this last layer before we stop, passing inputs through the network is this layer here, right? Layer M. And so what I'm doing here is saying, what if we want to compute the derivative of the loss with respect to one of these guys in the last layer? Okay, and this is actually going to be the easier case because the difficulty is like when you're trying to find the derivative with respect to a weight that's really, really deep in the network in terms of like it's one of the earlier weights. This is one of the lost weights. Okay, and hopefully you should be able to see that we're gonna, well, actually let me write it out. So d all dw. Okay, well, what is this thing? Well, and let me just make it really clear that I'm looking at this particular weight. It's the derivative of the half times k equals 1 to k of yk minus output k squared. And note that I'm not summing over data points anymore because I'm looking at a single, this is stochastic gradient descent, I'm looking over a single data point, right? There's nothing to sum over. That's why I have this. If I had multiple data points, nothing really changes. I would just start summing over multiple data points, but the rest of the calculation doesn't actually really change. Okay, now what is the output k? Okay, again, this is Wjim. This is going to be yk minus the sigmoid of net. I keep forgetting what I called it. I just want to make it really consistent. So net output k. Okay, and recall what is net output k. Maybe I can make life easier by just copy pasting this guy. Maybe not. Okay, what is output k or net output k? Okay, so hopefully you're getting a little bit more comfortable with this, this notation. This is the sum. Okay, I'm going to use a subscript L equals 1 to h m plus 1. This is the number of hidden layers in the mth layer. The number of hidden nodes in the mth layer times the weights w. This is going to be k, right? Because we're looking at the kth output. Output k is going to be the weights to the kth node multiplied by, WKL from the mth layer multiplied by the output OM, the elf output from the layer. So if you're confused by this, go back and make sure you understand what net means. It's just the linear combination of the outputs from the previous, or the weighted linear combination of the outputs from the previous layer. The previous layer has HM units plus a bias unit. These are the weights that are going into the kth node, right? We're looking at the kth output, OK, and the output from the previous unit is OL. Right? Now, the reason I'm writing it out in so much detail is because I want you to notice that we're taking the derivative with respect to WMJI, right? Now that means that you can throw away basically everything not to do with the jth output, right? Because WK, the derivative of WK with respect to this JI term is going to be 0, right? So all we care about is just the jth term in this summation. Which is WJL MOLM squared. Okay, so all I've done is this summation goes away because I'm taking derivatives with respect to the jth term, and the jth means the jth node, and so we can throw away all the other nodes that aren't equal to j. And so here my weight is just WJL, where L is going from 1 to HM plus 1. Okay, and this guy is just the sigmoid of net output j. Okay, so the reason for rewriting this so many times is you don't need to do this every time. I just wanted to make it painfully clear that why I'm throwing away one of the summations. Okay, well, why I'm removing the summation, because we only care about the jth output. Now, this gives us a hint of what we can do to compute the gradient. Okay, well, if we know that computing this derivative is just computing the derivative of this guy, well, we can use the chain rule to rewrite this as sorry, I'm going to write OJ instead of output J, just to make life a little bit easier. And so this is using the chain rule. Okay, and this is using the chain rule, kind of that advanced chain rule where we had 3 terms. Okay, but I mean, what I want you to just pay attention to when we go back to what we did first is, when we had this function that had 3, well, actually, look at this chain rule, the simple chain rule here, right? All we're doing is computing like the derivative of this f of g of x. So it's kind of like fractions, right? The dg and the dg cancel out, and we get df of dx. Okay, and similarly, what's happening here is we're computing this f of g of t of x. What we're going to do is df of dg, dg of dt, dt of dx. So it's kind of like fractions. The dt's cancel out, the dg's cancel out, and what we're left with is df of dx, which is the derivative of the entire right-hand side. So here, it looks kind of uglier, but it's exactly the same thing. It's kind of like fractions. All I'm doing is trying to find blocks that are easier for me to work with. So you can see it's kind of like fractions. I can get rid of this. These cancel out, and what I'm left with is the original thing that I wanted to differentiate. Now, why are these guys easier? Well, hopefully you can see that, what is the the first guy, okay, the derivative of the loss with respect to sigma net output j, well, that's like taking the, so I'll just do it here to make it clear, dLdW d sigma net oj. Well, this is like the derivative of the function half yj minus sigma net oj squared, right? So it's like taking the derivative with respect to x of the function half y minus x squared. It's really simple, right? It's just going to be the 2 comes down, negative comes out the front, negative y minus x. Right? Hopefully you see that. That's why we want to use the chain rule. It makes taking derivatives of these guys really easy. So let me write the result here. So this guy is going to be negative y minus x. So our y is yj. Our x is actually sigma net j output. Sorry, output j. Okay, that's the first term here. Gives us this. The second term, let me just get rid of this stuff. And you know, it's a struggle to kind of teach this, you know, in a video because there's just so much going on. It's not particularly hard, but it's just like the notation is kind of ugly, and there's a lot of things going on. It's kind of hard to keep it all on the same page. So bear with me, and hopefully you're kind of writing along as I with me, so it's not confusing you too much. Okay, so we computed this first derivative. The second derivative is the derivative of sigma net oj with respect to its argument. So this is like, what is d sigma x with respect to its argument? Well, we know sigma prime x is just sigma x 1 minus sigma x, right? So when I differentiate sigma of something with respect to that something, right, I'm just looking at the derivative of the sigmoid, which is in this case going to be sigma net, so this is the second term, oj 1 minus sigma of net oj. Okay, that's the second term. And finally, the last term is the derivative of net oj with respect to the weight jim. Well, look at the net oj, it's just the summation. And wji is only going to come up in one term, right? This is net, let's write it out just to be really clear, is the sum this is an L, M, O, L, N. So if we expand the sum, it's going to be wj1, m, o1, m, plus wj2, m, o2, m, plus, all the way up to wj, hm plus 1, o, hm plus 1. Okay, so it's pretty ugly, but all I'm trying to show is that when we're taking the derivative with respect to one of the weights, all of these terms are going to be 0 except for one of them, right? So if I was equal to 2, right, we're differentiating just this really simple thing. And so derivative of this with respect to the weight would just be the output for that particular, associated to that particular weight. So this is just going to be O, the output of the the ith output of the previous layer. Okay, and that is basically it as far as the derivative goes. Okay, so let me clean this up a little bit. Okay, let's write it out again. Well, this is going to be negative yj minus, so what is sigma net OJ? Well, sigma net OJ is just literally the output, right? So if we look here, sigma net output 1 is O1, so OJ is going to be sigma net output J. So these sigma net OJ terms are just the output of the jth unit in the output layer. Okay. Now I just want you to be, I want to be really clear, right? I've written this using some slightly different notation to what was in the lectures. The OJs without any superscript are specifically outputs of the final layer. This output here with a superscript M is the output of the previous layer, right? It's the output coming from the ith input from this layer into this network, into this particular layer, right? So OIM, right? So if I was equal to 2 and we're computing W3IM, right? Imagine that this is the gradient we're interested in. So here is the third right? This is the connection between the second input in hidden layer M and the third output unit has a weight W32M. So when I'm talking about O2M, I mean the second output of the previous layer, right? So this, in this case, it's O2M. It's the output associated to this particular node. Okay, so always go back to the picture and try to just figure out, just, does this make sense? Basically, it's just saying that the derivative of the of this weight is proportional to the output of the ith unit in the previous layer, which makes sense, right? Because this is connecting us to that node, right? And this is often written as just simply minus delta output J times OIM. Okay, so this term here at the front is well, actually, it's just this term here inside of the brackets is usually called delta output J. And delta output J is just another way of rewriting the negative of the derivative of the loss function with respect to the value net output J. Okay, so sorry, I just realized that might not be very clear. DLDW, right? Using chain rule, this is just DLD with respect to sigma of net output J times D sigma net output J with respect to output J. So I can use the chain rule to get rid of these guys and compute this derivative. So this first step in computing the derivatives where we had these two terms, this actually gave us the derivative of the loss with respect to the net. Okay, and so most commonly you'll see this referred to as delta output J. Okay, so what does that mean for us? Well, and by the way, this is, hopefully this is not too confusing. This is just notation. If you're not comfortable with it, just stick with the original notation up here. That hopefully is pretty clear. So this tells us that the SGD update is WJI m, right? Remember, this is case 1. So if this is an output node, the update is going to be, so it looks really ugly, but it's just saying that the jith weight in mth layer at iteration t plus 1, right? We're going to be updating these guys over and over, is going to be the old value at iteration t, okay? And gradient descent is, we take minus eta times the gradient, this gradient here that we just computed, okay? And since this is minus delta output j OIM, this is going to be plus delta output j OIM. Okay, and this is basically the stochastic gradient descent update for case 1. Okay, and all that work is actually, it looks really complicated. I kind of went through a lot of steps, but actually it's a pretty straightforward application of the chain rule, that we've seen a few times already. Okay, so that's case 1. That's actually the easier case. The harder case is case 2. So let me just motivate case 2, right? We just computed the gradients. Well, actually, let me draw it again, just not to keep using the same messy picture. Okay, so if you imagine that the output layer is here, so these are the output nodes, output 1, output 2, output 3 to output k, and this is hidden layer m. So what we did was just compute these weights, the gradients of these weights, right, the WMs. And that's really simple because, so this is LDW. We're trying to compute the gradient of this guy with respect to these weights in this layer. The reason that's easy is because the weights are really, like, if you think about them as distance in the graph or in the network, they're really close, right? The difficulty is when we look at, let's say H3, for example, which is really way back in the network, right? There's a bunch of hidden layers, and we start looking at the, the weights W3 or W2 or W1 or W0, right? Any of these weights, or any weights really prior to the output weights. These are called the hidden layer weights. Now, the reason this is more difficult is because the connection to the loss function is going to be more complicated in the sense that there's going to be, like, if you think about the, well, let's just think about this weight, HM minus 1. So this is the second to last layer. And let's think about this weight here, right? How do we take the derivative of the loss function here with respect to this weight here, right? Because think of like, what is the derivative? The derivative is saying, so what is the derivative actually telling us? The derivative of the loss function with respect to a weight is saying, how does changing Wji by a small amount affect the loss function L of W, right? So that's what a derivative is. A derivative is the sensitivity of a loss function or a function that you're trying to, understand with respect to one of the variables. Now, if you look at this Wji, right, look at the path this thing takes. Well, it goes here, right, and then we compute a weighted sum in this node, right, and then what happens is, what happens here is we compute net, which is a, it's a, sorry, let's say this is, you can kind of see why this is so difficult. It's because there's so many subscripts. This is the second node, so this would be W2L O O n minus 1L. Okay, so this weight, Wji, is going to be one of the weights that gets caught up in this summation, right? And then this will give us O2M, right? Then what happens to this O2M guy? This guy goes into all of these output units, right? And it gets taken into its own summation. Each one of these guys computes a summation and takes the sigmoid of that. So what I'm trying to illustrate is that the effect of Wji is going to go through here, and then it's going to go out to a bunch of other output units. So this question becomes really difficult because it's like, I'm trying to explain the effect of LDW of something here. Well, I have to try to explain the effect of this guy on all of these units individually, and then try to figure out the effect of all of these units on the final outcome. And if you compute weights in previous layers, there's more and more paths in the graph to reach L. So this is really the way you should think about it, is that think about a graph problem and think about all the paths that can be taken from this value, like from using this weight to get to this point. And as you increase the depth, the number of paths is obviously going to grow massively. Okay, and that's kind of the difficulty with this thing. So I say it's difficult. It's actually not too difficult, but it did take some time to actually, backpropagation was kind of this huge discovery. Actually, it was rediscovery. It was around for a long time, but nobody had thought to use it until I guess Jeff Hinton came along and applied it to neural networks. So let's actually describe case 2, which is the case where the weight Wji is actually a weight in the Gth layer, where G is some layer that's not the output layer. Okay, so in other words, we have let me draw the picture. Layer G plus 1. Here we're going to have a bunch of neurons. This is going to be HG, many neurons. We're still going to have our bias. And then layer G plus 1 has some other neurons and its own bias. Okay, and the output is, somewhere here. Okay, so there's a big distance in between. And we're looking at this weight, for example, Wji G. Okay, and in order to be able to describe this derivative, okay, let's just make sure we define a few variables. So what happens here? This is OJ, right? Wji, J means the node in the next layer it's connected to. So this guy must be node J. It's going to have output sigma net G plus 1 J, okay, which is, let me just erase this some away. It's going to be the sigmoid of the sum of HG plus 1 many terms, WJL G OGL. Okay, so nothing new here. I'm just writing out the terms in the the terms in the neural network computation. And what I want to define here is that this output, right, this OJ, what's going to happen is that it's going to go into layer G plus 2. Let me just get rid of this output. layer. You can imagine that the output is really far away, somewhere to the right. And the next layer is going to be layer G plus 2. And here we're going to have layers. So G plus 2 is this guy here. And it's going to have its own bias. And you can imagine that this particular OJ is connected to each of these guys, right? And the weight here is going to be W1 J G plus 1, W2J G plus 2, W3J G plus 2, and this is W H G plus 2 J. Yeah, that looks right. Okay, so all I'm saying is that these are the weights connecting the G plus first layer to the G plus second layer. I'm calling them this. And I want to also clarify that at this point here, right, what do we compute? We compute net G plus 2, 1, net G plus 2, 2, and so on, right? G plus 2 H of G plus 2. Okay, so what I'm trying to describe here is in the next layer, right, we're trying to compute the gradient with respect to this weight. Well, this weight is connected to this output OJ. This output OJ goes into the next layer after that, the G plus second layer, and it touches all of these guys, okay? So what I'm trying to do is trying to define all the terms that are going to be connected to WJI. And actually, what we'll usually call this is, what we usually call these elements that are connected, we'll call them the downstream variables. Okay, and these variables are downstream from the layer G plus 1 neuron J. Okay, so all of these guys are downstream, and the reason I'm using downstream, it's because some neural networks have weird architectures where this guy could be connected to a previous layer, or this guy could be connected to, like, it skips the G plus second layer and it goes straight to the G plus third layer. So I'm just going to use this term downstream to mean anything that's connected to OJ is going to be in this set. Okay. The way I've drawn it looks like it's just the things in the next layer, but just keep in mind that this could be anything in the network. Okay. Okay, so that's kind of the setup that I want you to keep in mind, and maybe just take a print screen of this and put it up because I need to use a new slide, and I want to compute the derivative with respect to this weight that's inside the network. I'm going to use the chain rule to rewrite this as the derivative Okay, I can use the chain rule to do this, and basically this will become clear in a minute why I'm doing this. But you should see that it's kind of easier to work with these quantities, and you'll see why in a minute. But all I'm saying is that we want to look at the derivative of this weight, the derivative of the loss function, which is down here, with respect to this weight. So we can look at the effect of the net of this neuron on the loss, and then times by the effect of this net of the weight, right? That's like, the derivative here is computing the sensitivity of the loss function with, the sensitivity of the loss function on the weight. We can split that up into two sensitivity computations. Okay, and the reason I wanted to do that is now we can use the thing we talked about, the downstream thing. Well, if you look at how does the loss function get affected by net g plus 1j? Well, net g plus 1j is here. Okay, it's going to basically impact all these future nets, right? Everything in the downstream. So I'm going to sum over all the elements, I'm going to call them z, in the downstream of g plus 1j. And basically what's going to go in here is the derivative of the loss function with respect to so let me write it out and then explain it. Okay, so let me just explain what's going on in the brackets. The brackets is the expansion of this first derivative. Okay, the first derivative is saying what is the sensitivity of the loss? What is the sensitivity of the loss to this net g plus 1j value? Okay, well, this net g plus 1j value, right? What do we do to it? We take the sigmoid of it, then we pass it to all the future nets in the downstream, right? So what I can do is use the chain rule to sum over all the values in the downstream and compute the sensitivity of the loss with respect to those nets times the sensitivity of those nets to the net we're interested in, right? So this is just chain rule again, right? Except I'm doing it over all the elements in the downstream. Okay, now if you recall, right, when we did the case 1, I defined this delta guy, delta output j, as the derivative of the loss with respect to the output, the net of the output j. Okay, now you should hopefully see that this is going to be a recursive calculation, right? Okay, I'm just going to write C here to save the trouble. But this derivative, right, is the negative of delta g plus 2z, right? This delta just means the derivative of the loss with respect to any net in the network. Previously, we just talked about deltas in the output layer, but here we can talk about the deltas in any layer. And it should be easy to see that this is going to be recursive, because the way we do backpropagation is we start from the second to last layer, right? And we have the deltas from the output layer. So we're going to be just recursively computing these delta guys as we go backwards. Okay, so you can assume this term is something we already have. This term, d of net g plus 2, is, well, let me just do it up here to save space. Okay, so what is net of g plus 2z? It's, I can use the chain rule to break this up into two pieces. Sorry, that should be G plus 1. Okay, so again, if you're confused by that, look at the picture. I'm looking at the derivative of net G plus 2z. So I'm looking at the derivative of one of these guys with respect to the net in the previous one. Okay, so all I'm saying is it's easier to look at the derivative of this with respect to the sigmoid, and then look at the derivative of the sigmoid with respect to the net. Okay, so that's what I'm doing here. And instead of writing the sigma of net G plus 1j, I'm realizing that sigma net G plus 1j is just the output j term here. Okay, and then hopefully this should be pretty clear based on what we did in case 1, that this is just going to be wzj G plus 1, okay, times oj G plus 1 minus oj G plus 1. Okay, and this is an identical calculation to what we did before in case 1, right? Except that we're working on in a middle layer. But the derivative of net with respect to the output is just, net is the weighted sum of the outputs, so we just get the weight. And then the derivative of the output with respect to the net, well, this is the sigma of net with respect to net, so we just get this sigmoid kind of term outside, okay? So what goes here is wzj G plus 1, oj G plus 1 minus oj G plus 1. Okay. Now this looks really difficult, but I encourage you just to go through it on your own, and you'll see that it's actually identical to case 1. Okay, except with slightly different subscripts. Finally, this term here, the derivative of net G plus 1j with respect to the weight wjig is very clearly going to be oig, right? Because net G plus 1j is the weighted sum of the outputs from the previous layer, right? So taking derivatives, with the weight is all you're going to get is this oig term. Okay, now I'm going to write the gradient descent, the SGD update, right? Because now we actually have computed the derivative. Now, this summation over the downstream should hopefully, I tried to motivate it here by talking about the effect that this weight has on the future layers, right? And then we kind of made that formal, or formalized it in this picture, where we said that, this weight goes into this net computation. This net computation goes into all future nodes, okay? But in general, it just goes into its downstream, so anything it touches. And so we can compute the derivative by looking at the weighted effect it has on all these guys. Okay, and that's how to explain this this summation term in the derivative computation. So the SGD update is going to be at iteration t plus 1, it's going to be the old weight at iteration t plus, okay, and the reason it's plus is because there's a negative here, so minus is plus, eta, I'm going to rearrange this summation a little bit. I'll get the OIG term out the front. Notice that this is a summation over z, and these two terms here don't have any z's in them, so I can take them out. Sorry, this is j, this is I. Okay, and this gets multiplied by this sum over the downstream of the delta z g plus 2. Sorry, I'm switching it around. Okay, the weighted sum of the deltas. Okay, and we can rewrite this as wji at iteration t plus eta oig. So this actually is how we define delta j g plus 1. Okay, and this actually gives us the recursive definition of delta j g plus 1. Because if you think about it, we start off with the output layer, we compute the deltas there. The second layer, right, is going to be these guys are easy to compute based on the previous layer, and this summation is just going to be over the output nodes. Okay, so we already have those deltas, and we work our way backwards. If you think of these deltas, okay, delta well, let me just kind of right here. So delta Gj is the effect of net Gj on the loss, right? So if you think about how we defined it in case 1, the delta output J is it's the negative effect of the net output J on the loss. And for inner weights, it's going to be the effect of the net for that particular node on the loss, okay? And so you can think of backpropagation, like why do we call it backpropagation? Because what we're doing is recursively computing these delta terms and passing them back in the network in order to be able to compute weight updates for every single weight, right? All these weight updates are based on the deltas that are being passed back from the output layer from right to left. Okay, and that's basically it. I mean, I know it looks like a lot of work, but really all you need to know is 2 lines, right? The 2 lines, or 3 lines rather, are these stochastic gradient descent updates for the weights for the network, right? You pass in the input from left to right. You start off with case 1. Where you compute the simple gradient step update, right? And this delta J is just literally just this really simple target or Y value minus predicted value times predicted value 1 minus predicted value, to compute the to compute the weight updates for the output layers. And then once you're done with that, you've kind of started the recursion for the deltas. You can move your way back and start doing weight updates for case 2 for weights inside the network.